Thank you very much. So it's a pleasure to be here, and I want to thank the organizers for setting up a remarkable conference. So the people that we have, let me see, yes. So Jonathan Tan is the leader of this group, and then I've also received a lot of help from the other people in the group. So let me first just remind you as to why it is that massive stars are so important. They create most of the heavy elements in the universe. They energize the interstellar medium. All the different phases of the interstellar medium, ranging from the cold atomic gas to the warm ionized gas to the hot gas, are really get their energy from massive stars. They regulate star formation. Massive star formation really governs the evolution of galaxies. And recently, people have been also working on the fact that radiation pressure from these massive stars can drive the enormous outflows that are observed. And they may have reionized the universe. So what I want to do is it's really impossible to try to cover all the work that's been done in this field since the last PP. I want to apologize in advance for all the hundreds of people whom I will not be able to acknowledge in this brief remark. So I'm going to start off talking about some of the observational advances that have been made, and then I'm going to go on to some of the theory and contrast high and low mass star formation and talk about the various theories that were several years ago were prominent and are still under active investigation. So there we go. We begin by talking about the sort of parameter space that you can look at for massive star formation. So here we have the surface density in grams per square centimeter. On the other side here, we have it in solar masses per square parsec. So for example, here's 100 and here's 10,000. And then on this axis, we have the mass. So what you can do is, once you know these two parameters, you can work out the escape velocity. So here's 1 kilometer per second, up here is 10 kilometers per second. You can get the radius of the object here, for example, is a parsec, and this one here is 10 parsecs. You can also get the density and the free fall time. So for example, here at a density of 10, then the free fall time is 14 million years. Now, we can put some data on here. Here are data on various molecular clouds going from IRDC cores to massive star-forming cores and clumps. Here are IRDCs themselves. Over here are the GMCs. Here's this famous molecular cloud in the galactic center, the so-called brick. We can then go ahead and add on star clusters. And when we do that, we find that some of the more extreme star clusters, like here's the quintuplet, here's R136, and then when you get to extragalactic star clusters, you find that they actually populate a more extreme region of the diagram. I'm going to be focusing my talk mostly on this part of the diagram here, where we're going up to several thousand solar masses, and we're talking about surface density between 1/10 and 1 gram per square centimeter. But I will also briefly mention something about the galactic center, which is a little bit more extreme. So first, let me just talk about the infrared dark clouds. This was a major discovery previously, in maybe a couple of PPs ago, back in '96. And here is an example that people now are still analyzing. So you have that the infrared background radiation is being absorbed, and you find that molecular gas is then associated with that. Now, I have to say that with 20/20 hindsight, the theorists should have predicted the IRDCs, but we didn't. So I want to now talk a little bit about the dynamics of these. So here we have these clouds. You could ask, well, how do they fit into the overall picture? So this is the famous line width size relation. These are data gathered by Edith Valgaroun. And I should say I refer to this paper. You'll see it has a question mark at the end, and that's because Edith has been seduced by Planck. And so it's hard to get her attention for boring things like line width size relations now. But in any case, these data go, this is only 12 CO. Here you have the GMCs here, and here you get the high latitude clouds. And basically, you can see within a factor of 3 or so, there's the line width goes like the square root of the size. So what about these infrared dark clouds? If you look at clumps inside them, you see that they actually lie above this line width size relation. This has been known for a long time that massive star-forming regions do not fit on the line width size relation. So how can we explain that? Well, here's the turbulent line width size relation that which I showed you to start with. If you then ask, well, what about if you just consider virial equilibrium? You have this the observational virial parameter, which is defined this way, and it's of order of the kinetic energy. Actually, I should have put a factor of 2 in there. But I want to emphasize this is an identity. So far, there is no physics in these first relations here. That's just definitions. The physics comes in. If I go ahead and I solve for the line width, then this, again, is an identity. If you say, well, it's gravitationally balanced, so the virial parameter is Roy unity, now I have some physics in there. This predicts then that the line width will go like the square root of the surface density and the radius. And if you convert, so that we can compare here to the full width half max, you can see that a surface density around 100 solar masses per square parsec, you get a coefficient that is somewhat similar. So now let me make a graph where I divide out the size dependence of the line width size relation and just plot it as a function of surface density. So this is the part up here, which Heyer would talk about, and that's the virialized line width size relation. But then you have this other part here, which has nothing to, these objects here are not in virial equilibrium. And the GMCs are right in the middle. So what that says is that GMCs both feel the ambient interstellar medium, and then they're also the structures that house these objects that are denser. So then I just want to briefly remind you of the definition which we advanced at the last PP and PP5, and we assume that this defined that clumps form clusters, cores form stars. The core evolution goes from high mass starless cores, and then there are cores that actually have the precursors to high mass stars, and so far those are hard to see, and I don't know of any that have been actually discovered. And then you get high mass protostellar objects, and finally the final stars. So with the clump evolution, you can have a similar thing where you have a massive starless clump, a protocluster, and then a stellar cluster. But in fact, people who've looked for these massive starless clumps, and none have been seen that are very massive, say above 10 to the 4th solar masses, that have surface densities that are above about 1/10 of a gram per square centimeter. So let's go back to looking at how we can map these objects. So here is an infrared dark cloud, and if you then go ahead and you can analyze the extinction here at very high angular resolution, so it's really arc-second scale, and determine the surface density completely independent of the dust temperature, which is uncertain. And this method can work up to surface density of order 0.5 gram per square centimeter. And when Jonathan Tan and his student Butler worked on this, they then were able to work out what the distribution of the surface density was for clumps. These are the larger objects that might then form clusters, and the cores that are embedded in them. And here you have the power law index, and they were typically around 1.5 or 1.6, I guess. And that was similar to what Hendrik found a decade ago. And when you analyze the masses, you find that these objects contain many thermal Jeans masses. So how can we go about and try to look and identify the high mass starless cores? And here's where astrochemistry comes in if you look at deuterated molecules. So Fontani and collaborators have looked at various sources where they look at the N2D plus line and they compare that with the N2H plus line. And then if you have a very high deuteration, that just essentially means that you're high up on this line. So then the blue is the high mass starless cores, and then the green are the high mass protostellar objects. And you can see that by and large, the blue objects, the starless cores, are up above. Although there are some of these starless cores that are down here. And these actually, they call them warm high mass starless cores. But you can see when you actually look at the environment of these starless cores, you see that they're right next to more evolved stars. They're being irradiated, and that's why they're warm. So then just focusing on these regions here, this is really an excellent way to go ahead and pick out a sample of the high mass starless cores. So Jonathan then went ahead and did this, and this was a recent observation with ALMA. So he selected cores that had a high ratio of this, and here we have the N2D plus lines here, and then went about analyzing them. So the picture is that you have a core with the dense center and then surrounded by a clump, and they then just looking at the extinction map, they divided the region up in this way. And in this case, they got the sigma of the clump was about 1/3 of a gram per square centimeter. If they measure the mass of the core in two different ways, either from the mid-infrared extinction or from millimeter observation, they get similar answers, although he was very careful in trying to estimate the errors, and you can see that there are substantial errors here. So this is probably accidentally close. And then going ahead and analyzing these cores, he then can work out what the line width that you would expect from virial equilibrium is compared with the observation. And you find, in fact, that basically it's very consistent with virial equilibrium. Now, there are a number of assumptions, however, that went into this relation. First, the core was assumed to be in pressure balance with the weight of the surrounding clump. This also includes an estimate of the magnetic pressure, and that estimate is based on the assumption that the alpha and Mach number is unity. And then it also assumes that this ion accurately measures the line width, but as we heard from Hua-Bai Li, he reminded us of this work by Martin Hood from a decade ago, which showed that in fact ion lines are often narrower than the neutral lines. Here's another example of looking at a sample of data to try to see whether things are in virial equilibrium. These data here from Caselli and Myers are for the Orion, and you can they fit this with what they called the TNT model, thermal non-thermal core model. That was basically a precursor of the work that Jonathan and I did on the turbulent core model, and they basically are consistent with virial equilibrium. Then similarly, if you look at in the Cygnus X cores, these data here are consistent also with the work that we did subsequently on this turbulent core model. So there seems to be a lot of data which suggests that things are in virial equilibrium, but there's been some work by Kaufman and Pillai, and in this case also I think Paul Goldsmith, where they have found a lot of cases where the virial parameter is significantly less than unity. So here they have this factor of 5 around unity here, and there are a lot of sources that fit into this. But particularly when you look at these samples here from Bienen et al. 12, and then they have Duval, and also, they tend to go somewhat below. So you can ask, well, how can that be, that you would get a virial parameter that is much less than unity? So one possibility is that you could have a very strong magnetic field. Crutcher worked out what the maximum magnetic field was, and at very high density, say of order 10 to the 6th, you're over a milligauss. So maybe you have very strong magnetic fields. It's hard to get down to this low value of the virial parameter with such fields, however. There are also observational uncertainties. For example, you see that some of the lowest points here by Duval et al., they assumed that CO over H2 was only 8 times 10 to the minus 5. Other people have made estimates of that ratio, and certainly just from the abundance of carbon, you'd expect it to be bigger than that. So if, in fact, the abundance of the CO were larger, that would tend to move you in that direction on this diagram. It could be initial conditions. Maybe you just you have this core and it's formed, and then you've selected them in such a way that it's just after the turbulence has died out and before they've started collapsing. And so they're temporarily in a state of suspended animation, as it were. But once they do start undergoing pre-fall collapse, then they evolve to a case where the virial parameter is of order a little more than 3, which is way up here. So these things are certainly not in pre-fall. So it's going to be very interesting to try to understand in more detail how that happens. Okay, so what about observations of accretion onto cores and clumps? Here is an example of where you can look at ammonia absorption against a hypercompact H2 region, which is only 1,500 AU in size. So these white contours then are an absorption, these black contours are an emission. And this is a very good way of doing it because you actually now are getting extremely high resolution observations of what's going on. And here you can use methyl cyanide to go ahead and work out what you can see the sort of rotation in this disk. And they're able to get an estimate of the accretion rate, which is within a factor of a few to 10 of 10 to the minus 3 solar masses per year. And then it depends on how much of the sky is filled by the accretion. Okay, another example is some work by Lopez-Sepulcher et al., where they looked at a sample and they found that only about 13% of the infrared loud clouds, but a third of the infrared dark clouds showed infall. Nonetheless, they saw outflows in 75% of them. So that suggests that most of these clouds had active star formation, but only in some of them had the infall signature. The median infall rate was 5 to the minus 3 solar masses per year. But they estimated that the protostellar, they then looked at the jets, and then assuming that the jets reflected some fraction, like say 10 to 30% of the accretion rate, they estimated that the accretion rate onto the stars was actually much less than that. Then more recently, they found clump accretion at a fraction of the freefall velocity, that the infall velocity was some fraction f of the freefall velocity between 20 and 30%. So what you can show if you just take the mass of the clump divided by the freefall time, that turns out to be proportional to v cubed over g, which is then very reminiscent of the famous relation that Frank Shu worked out for isothermal collapse, where you have c cubed over g. And they inferred a clump accretion rate, again, of somewhat in excess of 10 to the minus 3 solar masses per year. Then, before leaving this topic, I want to mention this remarkable result, which was just announced by Pareto et al., where they have found a clump which has several thousand solar masses of 1 parsec, so it's around 0.3 of a gram per square centimeter, and it's undergoing quasi-static contraction. So that part is seems perfectly normal. However, they then find this very dense clump in it, which has about 1/10 of the mass, but it's only 0.027 parsecs in radius. The density is 2 times 10 to the 8th particles per cubic centimeter, and the surface density is 52 grams per square centimeter. And that, at least to my knowledge, is by far the most extreme example of a star-forming core that we know of, and it's going to be a real challenge, theoretically, I think, to understand that. Okay, one of the main advances that's occurred observationally since the last Protostars and Planets is to actually get unambiguous evidence for disks around massive stars. So in this case here, by Krauss et al., you actually have observations from the VLTI, and they find an accretion disk with a central hole, and they infer that the stellar mass is about 18 solar masses, and the flared disk has a comparable mass and extends out to 130 AU. And you can see this is on the several parsec scale here, and down here this is 20 AU. So the VLTI has done a remarkable job. There's some very interesting result recently by Eiley et al., where they looked at CO bandhead emission, which is then coming from much closer in to the central star. So it's presumably still accreting, at least from the sample that they got these objects from. So these are probably the high-mass protostellar objects. And 25% of the sample that they used show this CO emission. And all the spectra are consistent with Keplerian disks, and mostly they extend into the dust destruction radius. So the disks are detected even around O-type stars. The most massive one they mentioned is 57 solar masses. So here you can sort of see what they're able to see, and then they have the observations, and then they have a model here which fits it fairly well. So this, I think, is a very promising direction to go in to try to understand better. It's also this 25% then is a very important number. Why is it much less than 1? Another remarkable observation that was made was of a protostellar jet emanating from a star which, if it's they measure the luminosity, if it's a single star, that's 10 solar masses. And so here you have the thermal emission with the accompanying polarization, but then here you have 6 centimeter emission, and you can also see the polarization. So what this suggests is that massive stars have hydromagnetic outflows in the same way that low mass stars do. And only in this case, because we don't exactly understand what caused the synchrotron emission, but it does clearly indicate that you have a sort of a perpendicular magnetic field there, which is then presumably toroidal. A strong magnetic field has also been observed in a star-forming clump. And you can see these polarization vectors are very uniform, and they have this classic hourglass shape. So that suggests that there's a strong field. They actually went ahead and made an estimate from the Chandrasekhar-Fermi method. When I redid their calculation, I found that this was actually magnetically subcritical, which is not possible. You couldn't get a core if the magnetic field is too strong. On the other hand, if you were to just take an estimate of the magnetic field from Crutcher using his maximum field, then that would be consistent with having a supercritical core that was formed. Okay, so what about the theory? First, let's just talk about what is the difference then between high mass star formation and low mass star formation. So the first thing, as I already mentioned, is that a lot of these cores that are forming the stars can contain many Jeans masses. And a corollary of that is that in principle, these cores could be highly turbulent, so that they might still have large velocity dispersion. It's just rather than being thermal, it is turbulent. So at least that's a possibility. The magnetic fields may be less important. We just have that one example where we've measured the magnetic field and we're not sure. But there's a magnetic critical mass, and if you go ahead, and evaluate it, then using the median field from Crutcher's sample, then it depends, it's of order 4 to 32 solar masses at a density of 1 million. So once you get cores that are more massive than that, that means they necessarily are supercritical, and maybe the magnetic field is going to be less important than it would be in low mass star formation. Radiative feedback has been realized for decades that can be very important. So the force of radiation pressure can exceed the force due to gravity. And also, furthermore, protostellar accretion can continue after the star has reached the main sequence and has begun to create an H2 region. So despite all these differences, I've listed now, there's some very profound difference between low and high mass star formation. You can still ask the question, is it basically a scaled-up version of low-mass star formation or not? And that really then divides the theories. So there's several different models. One is the core accretion model, which asserts that, yes, high-mass star formation is basically scaled-up low-mass star formation. And the star forms with a mass that is related to the mass of its natal core, and it predicts that the IMF then is determined by the core mass function, and this is the basis of the theories of the IMF that we heard about yesterday. But you can ask, why doesn't the core fragment into many small stars? So if I said that it has many Jeans masses, why don't I make 100 little stars instead of one big one? Where are the protostellar accretion disks? So as I mentioned, there have been discovered that at least 25% of these massive protostars show disks. Well, but what about the other 75%? Okay, the competitive accretion model then asserts that the massive star formation is profoundly different than low-mass star formation. So you start off forming a low-mass star in the same way, but then the low-mass star, in moving through the clump, which is growing by accretion, just accretes mass by tidally modified by de Hoyle accretion. And the challenge here is that as Bonnell and company realized in one of their early papers, and then as we showed in more detail later on, it does not work in a turbulent medium. If the medium is virialized, then the accretion rate is just too small. Magnetic fields and wide-angle winds are going to reduce the accretion rate, but these have not been included in the simulations. Now, a challenge then to both theories, both this theory and the core accretion theory, is why doesn't radiation pressure halt the accretion? So a third theory, which then doesn't even have to worry about the radiation pressure, is that massive stars form by direct collisions of lower mass stars. So then they don't have to worry about the radiation pressure at all. And recently there's been some very interesting work which has talked about stellar collisions after the stars have already formed. So this stellar collision model is very distinct from these in that it's talking about collisions while the stars are in the process of formation. And Asana et al. Have shown, just from studying the high-mass binaries, that you expect a significant fraction of high-mass binaries to merge during their lifetime. And Mokel and Bonnell have done a theoretical calculation to show that if you start off with triple star systems, you might wind up having them merge. And Fuji and Portuguese-Fart have looked at hierarchical clusters and again have talked about how, as they evolve, they will have stellar collisions over the several million lifetime of the stars. Now, simulations that include, so I'm now getting back to this original theory where I want to do it while they're forming. So I include both gas accretion and end-body simulations, show that these stellar collisions are unable to affect observed clusters, either intermediate mass ones like Orion or more massive ones like the Arches. Okay, so going back to the core accretion model, as I mentioned, one of the challenges is how do you wind up suppressing the fragmentation? Why don't I make 100 little stars out of 100 solar mass clump instead of one big one? So Mark Krumholtz suggested that this could be as a result of radiation feedback, that essentially the radiation from the star would heat up the surrounding gas enough to suppress fragmentation. This was confirmed by a number of simulations that we did. Mark and I then went ahead and suggested that there would be a threshold of perhaps a gram per square centimeter that you would need in order for massive star formation. So if I get to this point, then I heat up the gas enough to suppress the fragmentation. There is some evidence for this in the work that I cited before by Lopez-Sapolker et al., in which they found that if you are at low surface densities, then only a small fraction of the cores had high mass protostellar objects, whereas as you go up to higher surface densities, then you get a much higher values. The typical value for the surface density they got was a little bit lower than the one that we had estimated, though. Now, magnetic fields can also suppress fragmentation, and when they have them both together, they're even more effective. So here I've shown a result from Benoit Commerson and his collaborators. We also got a similar result with Andrew Myers. And we essentially, you find that in this particular case, here's the typical mass to flux ratio. Here's where the magnetic field is very weak. And you can see that with the typical observed mass to flux ratio, there's much less fragmentation. Okay, so how can we test these models? Jonathan Tan's student, Yichen Zhang, has done some very nice comparison. Here I'm showing some observations from Gemini, and then also from Sophia at a particular source. And then you can actually then go ahead and try to model that with the turbulent core model. So this is a cartoon of the model where you have an outflow cavity, you have a central core and a surrounding clump, and then here's the line of sight. And Yichen considered several different models, and here you can get the SED and compare it with observations. And here I think this is a particularly powerful diagnostic, which will become even more useful as we get more high resolution data, where you look at the flux profile along a particular direction. So you have different wavelengths here in the mid-infrared, and then you just can compare your model with that. That's going to be, I think, a very powerful way of trying to discriminate the different models. So in competitive accretion, Rowan Smith and collaborators then have pursued similar types of work where you do detailed calculations of what you would expect observationally. And here I just took out one of their figures showing how as you go to higher resolution, the HCO plus and N2H plus are going to vary systematically. And this just, again, shows you the possibility of doing this detailed spectroscopic modeling that should be very powerful in trying to discriminate among the models. There are some related models to competitive accretion. One is the so-called fragmentation-induced starvation, which basically is competitive accretion, but then you stop the competitive accretion by having, when the accretion flow is so dense, stars form in it and grab all the matter before it can get into the center. Eric Quito has worked on a model of massive star formation where he basically has the accretion occurring due to Bondi-Hoyle. So overcoming the radiation pressure, there have been a number of theoretical suggestions. First of all, disk formation. Then you can have the beaming of the radiation. And essentially, if you allow for an outflow cavity, then this radiation leaks out and you get much less radiation pressure. And the simulations have been done by a number of people, particularly by Rolf Kuiper and collaborators. And then we also did something on windblown cavities, which showed that this enables the accretion to continue. The role of the Rayleigh-Taylor instability is still under dispute. We find that it is effective. Rolf and collaborators find that it's not effective. But ongoing simulations, I think, will address that issue. So, what's the right answer? Is it core accretion or competitive accretion? Of course, there's also the even more exciting possibility that the new observations will show that it's none of the above. So here are some of the questions that observations, I think, will be addressing very soon. Does the IMF mirror the core mass function at high mass? There's some preliminary, very tentative evidence for this a decade ago, but ALMA, I think, is going to do a very decisive on that. Are disks always present in high-mass protostars? So as I mentioned, Eiley et al. Found it in 25%. If you look at this high spatial resolution observations, then both the continuum and the spectrum with theory. That's a powerful technique. Then you can go ahead and actually look at the, you have the initial mass function. You can also do the protostellar mass function and corresponding to the protostellar luminosity function, which is sensitive to exactly how the protostars form. Is the IMF at high mass universal? So interestingly enough, recently it's been shown that the IMF in Sagittarius A star, which is a very extremely different star-forming region than most, is similar to the saltpeter mass function, although a little bit flatter. What about the origin of very high mass stars? There's been some evidence now that stars more than 150 solar masses can form. How is that possible? Can massive stars form in isolation? There's recently a paper looking at this in the LMC, finding several potential examples. So then simulation, I think, is going to make a big advance. Well, you can ask, why is it that after 10 years, or 15, well, yeah, 10 years, we still have this debate going on between people on the one hand who do core accretion models and people on the other hand who do competitive accretion? Why don't we know the answer? Well, one of the things that underlies this is if you go back and look at the initial conditions, a lot of times the competitive accretion simulations start off with very smooth initial conditions, and they do not find any pre-existing cores. What we tend to do is first drive our initial conditions so that we actually have some pre-existing cores, and then we turn on gravity and allow them to collapse. But both of those are very artificial. What you really want to do is start off with a large enough simulation so that the turbulence itself consistently cascades down, and instead of putting in the initial conditions by hand, they come in from the physics. And that, I think, will be decisive, at least on the theoretical side. Then you want to include the complete physics. So include, we have ideal MHD, you'd like to go to non-ideal MHD. Allow for the fact that radiation, after all, does have a spectrum. Include the ionizing radiation and protostellar outflows. So with ALMA and more powerful simulations, I think the future will be revolutionary. Thank you.
Thanks for a very stimulating talk. That was fantastic. Lots of questions, undoubtedly. I would like to organize the questions a little bit different by see whether we can get somewhat more people involved by people lining up actually at the microphones that are standing in the middle and on the sides here, and there are also two over there in the columns. Because sometimes it's hard to see where the hands are actually being raised. And I think in this case we might try to get actually more people involved in the questions. I would also in particular like to encourage some of the younger people to move to the microphones and ask a question. So let's start off the discussion. I see Doug already lined up there. Go ahead.
I still think of myself as young. So Chris, the key issue in the core mass function that you bring up. So one of the problems I've always had is you define it theoretically, and I agree with you. I like the idea of a core being a single star. But observationally, I have to figure out how to do that. And observationally, when I'm thermal, I might imagine that I'm only going to make one. But when I am turbulent, it's really hard to know. So I think I can go into Perseus and break up the mass into lots of different ways if I include turbulence. It sounds to me like what you're really saying is that when we look at the core mass function, we should be looking also at the column density of the core, because a core that happens to have a lot of mass but is low column density isn't going to form a single object because of this fragmentation. Is that correct?
Well, that's our theoretical expectation, and I agree. I think you're raising a very important point about trying to pin down what the definition is. I should also say that in terms of the core, it's not really that it's going to make just a single star. You certainly include multiple stars. But in addition, if you start off with a core that's, say, 100 or 200 solar masses, the densest regions could be very small. And you might start forming some low-mass stars also. So you're likely to get low-mass stars in addition. The question is, which I agree from your point of view is very difficult to address in advance, is under what conditions will most of the mass, or a substantial fraction of the mass that goes into stars, go into, one or maybe a binary, two massive stars, as opposed to a whole bunch of little ones. But I think my hope is that with ALMA, as people are able to look at these cores, that it would be possible to come up with observational ways to see if there's a way to map it from there to the IMF, or not. It could turn out that you find with more study that there's no relation.
Hey, Chris, over here to your right.
Oh, right,
Yeah.
okay.
I was going to ask a very similar question, actually, about you mentioned that radiation feedback as a massive star is forming can inhibit fragmentation, and then how does that gel with the fact that most massive O stars are in binaries?
I'm sorry, most massive O stars are what?
Are in close binaries that are close enough that they'll interact and exchange mass during their lives, short period binaries.
Right. So I should say that one of the things that's characteristic of all the simulations is that they have terrible resolution. And when you're talking about the formation of binaries. Now, in the very first simulation that we did, where we formed a massive star, we in fact did get a binary, but we couldn't believe the details because at that stage, we don't have that much resolution. The question really is whether you can even get down to the place where you're going to form a binary which has 10 or tens of AU separation. And instead of forming, because you start off with a core that's much larger than that on the scale of 1/10 of a parsec. And the other possibility, as Claire Dobbs pointed out, was that you could just form a large number of low mass stars without any high mass star. So this feedback, the thermal feedback and the magnetic fields together do seem to be very effective in preventing that subfragmentation.
So on what kind of scales do you need the feedback, sort of the radiative feedbacks to be effective?
Yeah, so the radiative feedback, we tried to estimate that, and that's how come we got the 1 gram per square centimeter. And there was actually another consequence of having this very high surface density, which is that meant that the actual density was very high, the accretion rate was high, so that even a 1 solar mass star, the accretion luminosity could be 1,000 solar luminosities when you get, and so that, and then of course means that this very high luminosity, you can then irradiate a larger volume.
Oh, yeah, so how large is that in physical scale, sort of that's
Well, unfortunately, it depends on the details, but it can go out to a border 1,000 AU. And then on the larger scale, the magnetic field tends to be more effective.
Bob?
Yeah. I can't hear you, Rolf, it's not on. Yeah, shout.
So, I was about to raise a point of caution on the virial theory, but I think I should say something about the inhibition or non-inhibition of radiative feedback on massive star formation. I think you were selective in your examples, because there are also calculations with radiative feedback that do show that yes, fragmentation is induced, but not completely prohibited. Work by Thomas Peters, for instance, also with reflective fields. I mean, you can reduce the level of fragmentation by a factor of 2, but usually not much more. So I think it's relatively easy to form a cluster around a high mass star and to form also binary stars. So that is one point. The second point, I think, would be if one looks at the work by Protostars Planets VI, he cautions very strongly on the very simple application of the virial theory based only on the volumetric terms, right? These clouds are not very good. What shall I do? It's not working. Go to the mic. All right. So if the mountain doesn't come to the prophet needs to go to the mountain. Okay, I was to caution on the, well, I had 2 points. I think,
Maybe you can summarize them.
yes.
That's for
So the actual point I wanted to raise is on the usage of the virial theorem. I think the very simple application where you take a spherical cloud and you say it's homogeneous, that is not applicable for a typical molecular cloud. It's much more complex. It has a complex density and velocity structure, and in addition it has surface terms, right? I think the surface terms should not be neglected, as Javier Ballesteros has been shown. These things morph in a complex dynamical environment. So just placing analysis.
Can you shorten it a little
Yes,
bit?
almost done. On very simple volumetric terms, I think that can be wrong by factors of many.
Well, I completely agree that if you look at any one object and you want to compare it with a virial term, you have to include all the terms, including the time-dependent term, the surface term, and so forth. Nonetheless, it provides a way of assessing the effect of gravity. If you look at the average value of the virial parameter, that I think is very significant. As I mentioned, in many cases you do find that it's of order unity, and then if you want to have a large sample of objects where it is systematically very small, you have to understand why that is. And I mentioned several possible explanations. But as I emphasized, one of the explanations is not that it's in free fall collapse.
But then maybe adding the surface term would add another explanation to the observations.
I disagree with that. In the work that we did, in the basic turbulent core model, we include the surface term. And in fact, then the virial parameter is several. For a singular polytropic sphere, the virial parameter is actually several. And the only way we got it down to being more unity was to include the magnetic field.
Okay, good. This sounds for a good coffee discussion. I just want to check, is there anybody up on the balcony who wants to ask a question? No? Nobody there? Then we continue here with the line. So please state your name before you.
My name is Hiro Takami from Asia, Taiwan. And my question is about the observation of the disks. And we are sure these are direct proof for the presence of disks. But actually, I don't think it's a direct proof for mass accretion from the disks onto stars. And definitely the latter is a more important issue, so to understand the high mass star formation. So I just want you to add a little more explanation about that.
Wait, so you're saying that, I mean, most of the data I was describing was formation onto the star disk system, and were you asking then, there's another question, is once you have the matter in the disk, how does it get onto the star?
That's right.
Yeah, so I agree that that is an issue. That's, I think, one of the things that's exciting about the Eiley et al. Observations is that now they're observing the properties of the disk within 10 AU or so of the star. So that's going to give us some evidence about that.
Okay, we have two more questions here.
Yeah, hi. My name is Rolf Kuiper. So you mentioned the controversy of the importance of the radiative Rayleigh-Taylor instability. And I just want to mention that our simulations were also confirmed last year by two independent research groups. One's the Owen et al. Simulations, which was Monte Carlo radiation transport, and then by Harris et al. 2012, which used Monte Carlo with hydrodynamics. So, and they also confirmed that the radiative force is underestimated if you use flux-limited diffusion, the Gray approximation.
Okay, I should say that I agree that the flux-limited diffusion that we use does underestimate the force. And as I said, we're now going to improve on that, and then we'll see how our results agree. I did cite some other, particularly Zhang et al., who is not collaborating with us, that also found that you do get a really radiated Rayleigh-Taylor instability. So I think it's an open and interesting issue.
I'm Mike Kuhn from Penn State. In dense young stellar clusters, there's occasionally evidence that the massive stars form later than the low mass stars. An example of this might be W3 in a study by Feigelson and Townsley. And I was wondering if you could comment on how the presence of very active formation of low mass stars before the massive stars would affect these massive core processes.
Yeah, so that's a good question. I did not address it. I think that one of the things you have to keep in mind about the so-called universality of the IMF is that that is true only when you average over space and time. And what you would expect when you're forming in a region of high mass star formation, these regions are generally regions of very high column density. If you ran the clock backward, clearly they would be at lower and lower column density as you go backward in time. But we know that under those conditions, you can still form low mass stars. So it is certainly the case that I would expect you to have low mass star formation going on until the high mass star formation turns on. And this low mass star formation presumably will be contributing to driving the turbulence in this high mass star forming region.
Okay, good. Well, let's thank Chris and Jonathan and their team for a fantastic